Okay, so this is unit 4, number 13. So the question says, suppose the volume between the shells in problem 3 is completely filled with dielectric material having a constant 4. So in problem 3, the question was that there were two spherical shells. So if we say that the capacitor of that of those shells is C naught, then the new capacitance of the dielectric would be CD equals kappa times C naught. And then we know that kappa equals 4, so that would equal 4 times C naught. So that's part A. Part B asks, with the same delta V between the shells, in both cases, find the ratio of the charge stored in the situation to that stored in problem 3. So we know that C equals Q over V, delta V. So in the initial situation, Q is just going to equal C naught times delta V. We know that in our new situation, the capacitance is going to be 4 times the original capacitance, and delta V would be the same because that's what's given in the problem. So the ratio between the two charges would be 4 to 1. And then part C asks, suppose our dielectric is a liquid and we only fill the volume between the shells halfway. Find the ratio of the capacitance in the situation to the capacitance when empty. So in our new situation, it's two shells, spherical shells, and it's only filled halfway with some dielectric material with a dielectric constant kappa. So first we have to find the electric field. So from Gauss's law we know that the integral of E dot dA is equal to the charge inside divided by epsilon naught. So we'll do this for both so first we'll calculate the electric field for the dielectric part of the sphere. So normally dA would be 4 pi r squared because that's the surface area and that's where all the electric field lines or all the flux lines pass through if we draw a Gaussian surface as a sphere. But we have to multiply this by 1/2 because only half of the sphere is filled with the dielectric material, and right now we're just trying to find so we're going to find the capacitance of the dielectric part and the capacitance of the empty part separately and then add them together. So we have to find their E fields separately first. So for the dielectric part, it'll be, well, for both parts, it'll be E times 1/2 and then 4 pi r squared equals Q over epsilon naught. So we know that the E equals Q over 2 pi r squared epsilon 0. And then we want to find the delta V for just half of a sphere. So then if we call this radius A and this radius B, then we know that delta V equals negative E dot ds, and we go from the distance of higher potential to lower potential. So that'll be B to A. And then if we plug in what we know that negative q times 2 pi over 2 pi epsilon 0, and then the integral b to a of 1 over r squared dr. If we continue this up here, then we'll get negative q over 2 pi epsilon 0 times negative 1 over r from B to A. And then if we solve that, these negatives can cancel out. So we get q over 2 pi epsilon 0 times 1 over A minus 1 over B. And if we simplify that, we get q over 2 pi epsilon 0 A minus, B minus A over AB. So that's the delta V for half of a sphere. So we know that the capacitance of the dielectric part will then be so capacitance equals Q over V, but we know that the dielectric capacitance is 4 times the capacitance of like nothing in it, so we'll do 4Q over delta V for the capacitance part. And if you plug in what we just found for delta V into that equation, you're going to get 8 pi epsilon 0 AB divided by B minus A. Then you want to add that. So to find the capacitance total of this half-filled sphere, you're going to add CD to half of the capacitance of C naught. And technically you should have found this in number 3. And if you didn't, then you can just do these calculations. Then all you have to do actually is just change here. You'll just do Q over delta V instead of 4Q over delta V, and then you multiply it by half because it's half the sphere. Actually, just kidding, you already did that. So yeah, just do Q over V. And then you're going to get that, so then half of the normal capacitance is going to be 2 pi epsilon 0 AB over B minus A. So if you add the capacitance of the dielectric to the capacitance of the empty part of this half-filled capacitor, then you are going to get 10 pi epsilon 0 AB over B minus A. And then if you solved for the capacitance here of a empty spherical capacitor, then you should have found that C naught was 4 pi epsilon 0 AB over B minus A. So if you divide the two, then you're going to get that C1 over C naught is 5 over 2, which is your answer. And that is number 13.